Okay, guys, good morning. The summer is over. I don't feel so sad, maybe a little bit. Okay, anyway, so it's a physics 1 class. I haven't taught this class for 4 years. Every time it's physics 2, physics 2, physics 2, and now every time I have to control myself, it's physics 1 class, finally. All right, okay, so where we're going to talk about laws and rules of classical mechanics. All right, so of course you can read lots of things, so what classical mechanics is designed to do, but actually the idea of classical mechanics is very simple, very straightforward. In simple words, essentially you have some mechanical system. It can be a car, it can be a bunch of particles, right, whatever, right, so. And then you know about that system something at the initial moment of time, some initial conditions, initial position, velocity, maybe something else, color. And then you want to predict the future of that system. That's it. You just want to predict where that system is going to be at any moment of time later. Where that system is going to be, and you want to know what that system is going to do. That's it. That's the whole classical mechanics. We just want to be like a future tellers. But of course, it's almost like there are fortune tellers which are trying to predict the future of people using some finicky rules. But in this case, we're trying to be almost like them, but we're using well-defined tools. We can call ourselves future tellers of mechanical systems, right? That's it. So that's the role of classical mechanics. And that's what we're going to talk about the whole semester. And of course, we need to know and be comfortable with all those well-defined tools. And of course, there are plenty of those tools because the world is quite big, right? And that's why we have the whole course of mechanics. And that's why all engineering students must be at least familiar with that, right? Because you're going to try to harvest that world. Anyway, but before we start discussing all those rules, we need to talk today about some very fundamental, almost like basic ideas, which you're going to use everywhere in physics 1, in physics 2, in physics 3, in all engineering classes. Now, let's start with those basic ideas which you will need to know pretty much throughout the whole, maybe even your life. All right, uncertainty, sig figs, units, and units conversion. Right. I'm still thinking to make sure that I didn't forget anything to mention about the course. So, you all know that physics, it's all, at the end of the day, it's all about measurements. It's impossible to avoid that, right? So, of course, theoreticians can predict anything they want, but still, at the end of the day, it must be confirmed experimentally. So it's all about measurements. And whenever you measure something, and let's say you want to write a paper or report or whatever, what you need to show about your measurements in order to avoid any additional questions. There are 3 things that you need to show, must show. Otherwise, people will start asking you questions. So what are those? 3 parts to the measurements. Of course, first of all, you need to show the actual number, how much of something you measure. 5, 10, 125. Of course, first of all, you need to show a number, obviously. So the measurement, let's say 13.2. Second, you can measure different things. You can measure mass, you can measure velocity, you can measure current, you can measure age, different quantities. And they're different, they're apples and oranges. So how do we express, how do we show to the reader, to the other person, what we measured? What do we use? Of course, we use units. We use units. That's the logic of using units, and that's why on the exam or any other things we demand from you, show units, show units. You need to develop a strong habit of doing this. Otherwise, people will start asking you, what did you measure actually, right? So we need to show. Second, show the units. Gram, kilogram, light years, right? And the last item, what else do we need to show? we need to show our experimental error. We need to show the level of uncertainty, because no measuring device can give you perfect measurements without experimental uncertainty. It's impossible. It's all in physics. It's almost like everything is approximations, right? So we need to show the level of uncertainty, your experimental error, right? So we need to show the uncertainty of your measurements. It depends on which device you use. Cheap device can give you larger experimental error. Expensive device can give you better results. Then it depends on your sloppiness or diligence, right? So maybe you made only one measurement, or maybe you made 10 measurements and then average to increase your uncertainty, right? So it depends, right? So it depends on many factors. So we cannot say what should be over here, but you need to show your experimental error, right? Okay, so you need to show that, but sometimes uncertainty is not shown. Like in most of the problems in our textbooks, uncertainty are not shown. So they show the number, no current is 0.1 amps or velocity is that, but uncertainty is not shown. Does it mean that uncertainty is zero? No. It just basically means that a certain convention is used. If uncertainty is not shown, most likely it means that that person assume that you are going to use the convention. If you, of course, uncertainty fits the convention, then we can use convention. What is that? First of all, what is the convention? It's just a bunch of old physicists got together somewhere in a nice hotel in Florida, right? And decided, okay, let's use this convention and then force the rest of the world to follow that convention. Essentially, it works like that, right? So, what is the convention in this case? Let's take this number. Let's assume that 13.2 grams is given without showing explicitly the uncertainty. According to that convention, uncertainty is in the last digit of the number. Don't ask me why. It's a convention, accepted everywhere in the world. Right? So if uncertainty is not mentioned, then convention, again, our number, uncertainty is in the last digit in 2 and plus minus 1 of that digit. So in this case, essentially it means that the actual weight is somewhere between 13.1 minus 1 and 13.3 plus 1. Convention, plus minus 1 of the last digit of the number. All right, so we're going to use this convention. Then let's assume that somebody wrote something which looks like this, 13.20 grams. It looks like what's the waste of ink and space adding that zero. But in this case, according to this convention, this zero is extremely important. Essentially, it means that this person now, invested more money, got a better scale, and now the uncertainty, the accuracy of the results went up. So now uncertainty is in the second digit after the decimal point. That zero is extremely important, and we shouldn't be trashing it. According to the convention, now uncertainty is in 0, plus minus 1. So still plus minus 1 all the time. So now uncertainty plus minus 0.01, which means that uncertainty, the actual weight is between 13.19 and 13.21. Right? So you got that point, you got the idea. Right? So then if you add additional 0, again, it means that, again, you have now better results. Uncertainty is in grams, milligrams, right? So plus minus 1 in the last digit, right? So that's the convention. And of course, that's what we're going to use in all these courses. As I said, most of the books, most of the problems in the book, they don't give uncertainty. They just give a number and expecting that you know this rule. So it's one way of showing experimental error. We can use uncertainty. But also there is another way. We can use what is called significant figures, right? And also very important idea, very important quantity, sig figs. So what is sig figs by definition? So let's say you have a number. Significant figure is the number of accurately known digits plus 1 at the end, which is uncertain. So number of accurately known digits plus 1, which is uncertain, the total number of those digits give us number of sig figs. Okay, example, because it can be confusing. Let's say we have a number 13.4. 1 and 3 are accurately known. We can bet all our money on these two digits. We know that they're exact, they're correct, they're perfect, accurately known. And 4 is uncertain, plus minus 1 uncertainty, right? So we have two accurately known digits plus 1, which is uncertain. So we have 3 sig figs of this number, right? Then another example. Let's say we added 0 at the end. So now that 0 emphasizes that uncertainty is over here. And now 1, 3, and 4 are accurately known. Again, we can bet all our money on those digits. Right? So now we have 3 accurately known digits plus 1, which is uncertain. So we have 4 sig figs, significant, right? So it's an alternative way of expressing your experimental error of the measurements. Uncertainty, sig figs. So we can use this rule to count sig figs. But sometimes, you know what, sometimes it's better to develop a set of rules sort of to speed up the process of finding sig figs. And now I'm going to show you 4 rules which we are going to use to count number of sig figs of this or that number. And usually the trouble is with 0. 0 is a troublemaker in terms of counting sig figs. If there is no 0, then it's very simple. Just count all the digits. But if there is a 0, then we have to be careful. And all those rules are about 0. 0 in the middle of the number, 0 at the beginning of the number, and 0 at the end. So all these rules about zeros, how to handle zeros, right? Again, to speed up the process of finding number of sig figs. So let's discuss those 4 rules. So the first rule is the simplest. Let's say there are no zeros. As I said, it's the simplest case. Just count all digits. For example, 1.234, no zeros, significant figures, 4 sig figs. Right? The simplest case. Now, what if there is a 0? Again, troublemaker appears. 0 between non-zero digits. 0 in the middle somewhere between non-zero digits. In this case, 0 is significant. We need to count it towards the total number of sig figs. So in this case, 2 accurately known, 1 uncertain, so we have 3 significant figures, right? So 0 in the middle, count it, it is significant. Now, next rule. Again, you remember 0 in the middle, 0 in the beginning, and 0 at the end. Now let's discuss zeros at the beginning of the number, leading zeros. And according to that rule, leading zeros before the first non-zero digit, basically to the left of the first non-zero digit, is those zeros are not significant. We're not counting them to count number of sig figs. I will explain the reasoning in a few minutes. So example, let's say we have 0.01 meters. So you see, first non-zero digit is over here, and to the left we have 3 leading zeros. And according to this rule, those zeros are not significant. So basically we trash them to count number of sig figs. In this case, we have only sig fig is 1. Number of significant figures is 1. Then, second example. So the first non-zero digit is 1, and then to the left, leading, we have 2 leading zeros. Again, they are not significant. We can trash them. So in this case, we have 2 sig figs. Of course, you can ask, so what's the logic of this rule? Why are we ignoring those zeros? I don't know, discriminating those zeros. Reasoning, here is my reasoning. So let's take this first number, 0.001. Can we rewrite it in a slightly different way, different form? Not a big deal, right? We can write it, for example, like 1 times 10 to the power of minus 3. It's still the same number, right? How else can we rewrite it? For example, using prefixes. 10 to the power of minus 3, it's a milli, right? So we can write it as, for example, 1 millimeter. So now, if I give you this number, do you have any doubts of how many sig figs there isn't this number. I doubt that you have any doubt. Obviously, you have one significant figure. In my opinion, this is the logic why all these leading zeros are not significant counting number of sig figs. You can easily replace them with some prefix or something else, right? So this is rule number 2. Leading zeros, not significant. So now we have only last option left, zeros at the end of the number. But in this case, we can have two situations still. Zeros at the end of the number before the decimal point, if there is nothing behind the decimal point, and leading zeros after the decimal point. Two situations. And we're going to discuss both of them because those are two quite different cases. Now zeros at the end. So next rule, trailing zeros after the decimal point. And now this rule shouldn't be surprising for you because essentially we discussed this case a couple of slides ago. Because those zeros, you see, for example, 3.20, you see trailing zero at the end of the number after the decimal point, and you remember why we added that zero, because we want to emphasize the level of uncertainty of this number. The level of uncertainty is over here, and it's a very significant, so it's a significant number. We count the zero towards the total number of sig figs. So we have 2 accurately known plus 1 uncertain. We have 3 sig figs. Trailing zeros we count. Leading zeros we ignore. Right? So different rules. So in this case, so we have 3 sig figs. Now this example. Now I mix. We have 2 leading zeros from rule number 2. So we are not counting those zeros. And we have 1 trailing zero. And according to this rule number 3, this zero is counted. So we have 2 accurately known plus 1 uncertain. We have 3 sig figs. Right? So it's a rule number 3. And now the last rule, again, 0 at the end, but now 0 before the decimal point when there is nothing after the decimal point. Now the last rule. So, for example, let's say somebody measured a length, I know, for the race, for example, 2,950 meters. And that person gives me this number. Okay, so I measured, here's the number, right? Enjoy it. If I start looking at this number, I can think different options, different situations. I can think in this way, maybe that person is very diligent and he measured accurately with the accuracy down to 1 meter, plus minus 1 meter. In that case, with that speculations, I can say, okay, uncertainty is in this 0 at the end. Uncertainty, plus minus 1. In that case, there will be 4 sig figs. 3 accurately known plus 1 uncertain, so there will be 4 significant figures. But also at the same time, I can think this way. Maybe that person didn't have a good measuring device and measured with the accuracy of 10 meters. Or maybe just measured a certain number and then round it to 10 meters. I don't know. So, but it's also possible. In that case, uncertainty will be in 5. So in that case, we have 2 accurately known plus 1 uncertain, and we have only 3 sig figs. So in the first situation, I'm getting 4 significant figures. In the second situation, 3 significant figures. It's a case of ambiguity. If somebody writes something like this, if you write something like this, you can confuse people unless you add some additional statement, unless you give additional information that my uncertainty is that, my accuracy is this, something like that. If you just give this number, you will confuse people. So this is the case of ambiguity. Rule number 4, essentially, don't use this form of writing unless you add some additional statement, right? So how can we avoid this ambiguity? Rewrite it in a different form. We can rewrite it using powers of 10 notation. For example, so if you want to show that you have 3 or 4, first, let's say 3 significant figures. You need to rewrite this number in this way. 2.95 times 10 to the power of 3. This 10 to the power of 3 doesn't give you any information about sig figs. All that information is over here. So you can see we have now 2 accurately known plus 1 uncertain according to our convention. So now everyone will know that accuracy is plus minus 10 meters, right? So 3 sig figs. In this case, no one will be confused. But if you want to emphasize that your measurement is significant, you have 4 significant figures, then of course you need to rewrite it in this form. 2.950, you're adding 0, times 10 to the power of 3. Now everyone will understand, this guy did a great job, and accuracy is plus minus 1. Now no one will be confused and there's no ambiguity. So this form, you can use it, but in that case, you need to make a statement. So what's the uncertainty? What's the accuracy? But if you write it like this, you don't have to add anything else. Okay, so these are 4 rules which we will use to count number of sig figs, because sometimes we need them. Okay, so now next, next the question. Okay, let's try that poll everywhere. Here's what I forgot to tell you. Usually, okay, we're going to use poll everywhere, every class. 1, 2, 3 questions every lecture. But first 3 classes of the semester, results of the first 3 classes of the semester I usually don't use towards the final result. Because still students register, students drop from the class, sometimes they have troubles with just registration to this poll everywhere. So first 3 lectures, okay, we're going to use it, but I'm not going to use this results towards the final score, right? So I think it makes sense. So I've been doing it for many, many years. But anyway, so let's try to use it. So the first question, first of all, can you see this question in your poll everywhere? Yeah, it's available, so it's activated. So we have 2 numbers. You see this and that. So you need to tell how many sig figs we have here and how many sig figs we have in the second number. And you see the options. Okay, I see I need to fix something. My animation slightly wrong. Appeared at the wrong moment of time. All right, why it doesn't show? It's supposed to show your results, the distribution of the results. This poll everywhere, yeah, it works, but in terms of showing what it's supposed to show, sometimes, actually quite often, it gives me a hard time. Okay, I can see it on my... Okay, so almost a delta function. Everyone believes in B, and only 2%, oh no, now 0% believe in C. Okay, so great. So it means that, yeah, it's not a rocket science. So it's some ideas, most of you probably even familiar. All right, so let's just quickly discuss. So first number, we have leading 0. According to the rule number 2, we are not counting those zeros, right? So trash it. Then trailing zeros after the decimal point, it's significant. So we have 2 accurately known plus 1, which is uncertain, but anyway significant. We have 3 sig figs. So 3 sig figs over here. Then power of 10 notation, it doesn't give us any sig figs. So we just need to look at this factor. So no zeros at all. So we need to count all these digits. So we have 4 digits. So 4 sig figs, right? So we have 3 and 4. This guy is supposed to appear later. I need to reanimate it slightly. I didn't notice. Okay, so questions like this, as I said, there will be sometimes 1, sometimes 2, sometimes 3 questions. I don't feel like using more than that. I haven't lectured for 2 months. My voice is a bit giving up. So now, next situation. Now, let's assume that we're doing some measurements. I don't know, measuring, let's say we want to calculate the resistance. We measured potential difference across a device with some amount of uncertainty or experimental error. Then we measured current, again with some amount of uncertainty and experimental error. And now we need to divide potential difference by the current to get the resistance. And the question is, what will be the amount of, what will be the level of uncertainty or experimental error in the resistance after dividing these 2 numbers? And so we need to learn those rules, how to divide quantities which have some levels of uncertainty. It's very, very important. Basically, we're touching error analysis, barely touching error analysis, which is essential in any experimental work. Right. So first, simplest situation. Let's discuss if we want to add two numbers or subtract. The rule is the same for both addition and subtraction. So the idea is, okay, probably I will just read. The final result is no more precise than the least precise number used to get the answer. In simple words, a chain is no stronger than its weakest link. So you need to find the weakest link, the number with the least certain, and use that level of uncertainty in your final result. In simple words. But finding the weakest link is slightly different when you need to add numbers or subtract or multiply and divide. In the first case, we will be looking at the level of uncertainty. In the second case, we will be counting sig figs. So first, adding and subtraction. And we need to look at the level of uncertainty. For example, let's say, let's say we have two numbers. So you need to find the level of uncertainty of the first number, then level of uncertainty of the second number, see which one is least certain, and use that level of uncertainty in your final result, rounding to those digits. So let's imagine this situation, just in order to describe the whole story. Let's imagine that I know me and you, we work for the same boss, right? And he gave us assignment. So here's the big rock, here's the small rock, measure masses of both of those rocks, and give me the final result, total result. Okay, I'm as a greedy one, I will get the big one, I'll give you the small one, right? So, and we go to measure those masses. Okay, I will find in some corner of my lab, let's say some poor scale, and let's say I measure the mass of my rock, 82 kilograms. Where is the level of uncertainty? According to the convention, it is in the last digit, in 1. So my uncertainty is plus minus 1 kilogram. Sloppy work, right? Right. So then you go and you'll find a nice scale, right, very accurate, and you measure your small rock, and it happens to be at 0.13 kilograms. So his level of uncertainty is very good in tenths of grams, plus minus 10 grams. So now if we add our numbers, of course, if I use the calculator will give us 82.13. Does it make sense? Obviously not, because I cross it out immediately. So, because from the physical point of view, it doesn't make sense. Why? My uncertainty plus minus 1 kilogram. His uncertainty, 10 grams. Who cares about his grams with my level of sloppiness? So basically, all his accuracy is buried in my uncertainty. So my uncertainty plus minus 1 kilogram determines the uncertainty of the final result. It doesn't make any physical sense to take care of all his great work, right? So basically, your result will be completely buried with my sloppy work. So in this case, the least certain is 82 kilograms, and this level of uncertainty in this first digit before the decimal point, must be used in our final result. So the level of uncertainty of the final result must be in this digit, which is determined by that number. So now, once we found out where the level of uncertainty must be, now we need to round that number to that digit, rounding. So now it means that we need to look at the next digit. It's 1. It's less than 5. So rounding is going to give us just 82. We just need to trash that 1 and 3. Rounding, right? You remember? So as a result, the answer is 82. But let's imagine slightly different situation. Let's say his number was 9 and 3, 0.93. For example, like this. Again, calculator will give us something like this. Now, uncertainty is still in this digit, but now rounding, look at the next digit, 9, larger than 5. So it means that during the rounding procedure, we need to add 1 to the previous digit. So it means that 1 must be added to these 2. So as a result, the answer will be 83. So first, find the level of uncertainty and then round. Don't forget about this rounding process, right? Now, great. Now I feel ashamed with my poor result. I found the better scale in a different corner of the lab. And let's say I measured now with better accuracy. Now let's say my result is 82.0. He's conservative. He stays with his scale, with that great scale. So now calculator will give us still 82.13, and still doesn't make, that number still doesn't make sense. So where is my level of uncertainty? I improved, but it's still, my uncertainty is in the first digit after the decimal point. His uncertainty is in the second digit after the decimal point. Still, his accuracy is buried in my sloppiness, right? In my uncertainty. So it's still, we're trashing his results. So I'm still the weakest link in our teamwork. So still, my result is going to determine the uncertainty of our final result. It means that uncertainty must be in this first digit after the decimal point. And again, rounding. Look, next digit is 3, less than 5, so we need to just trash it. So the answer is going to be 82.1 kilograms. So now this is the answer in this case. Okay, now I got into competitive mood. I decided, okay, I need to beat this guy, right? So I invested more money and I got a better scale. So now let's say I measured with accuracy to the second digit after the decimal point, 82.00, and he still uses the same scale. Which number is the weakest link? They are both either equally good or equally bad, right? So pretty much now both numbers are equal in terms of the level of uncertainty. So now, of course, our calculator is going to give us 82.13, and it's for the first time when the calculator is going to give us the correct answer. So now it's this is the correct, yeah. Yeah, it's here. It should be approximately. When I was, yeah, here it should be approximately signed. It shouldn't be equal. Yeah, it's strictly speaking kind of not a good idea. I just, when I started lecturing, I realized I should have changed that. Sorry, but again, you got the point. Now, okay, so I still didn't manage to beat him. So I invested more money. Let's say I got accuracy to the grams. Now, in our team. His result are the weakest, is the weakest link, right? So now his measurements is going to determine the uncertainty of the final result. So now it will be, of course, strictly speaking, it should be 82.130, but I immediately trashed that 0. So now still the same result, right? So you got the point. So, and now multiplication and division. Idea, philosophical idea, exactly the same. We have to search for the weakest link and then round the number. But now we're searching for the weakest link using sig figs.